Hello and welcome to College Physics 1, Lecture 27, Conservation of Momentum. In our previous lecture, we introduced the concepts of impulse and momentum. Momentum being mass times velocity. In this lecture, we're going to take that discussion one step further and introduce our very first conservation law in physics. Now keep in mind, laws are extremely important in the sciences. They represent the highest level of discussion or detail that we have. So this is an incredibly important discussion that we'll have, and as a result, we're going to do 3 examples in a row at the end of this lecture to really hit this idea home. To begin, we want to understand what conservation means and how we understand it comes about. To do this, we're going to run through a series of if this, then that statements. If, then statements. So let's start with our basic description of Newton's third law. Recall from the past that Newton's third law says that for every force, there's basically an equal and opposite force when there are objects interacting. So in the example you see on the right, there's 2 balls that are colliding. They exert a force on one another during that collision. Force 1 acts on 2, and force 2 acts on 1. Those forces, by definition of Newton's third law, must be equal and opposite. In other words, we say that they form an action-reaction pair of forces. Okay, so far this is just a restatement of Newton's third law. Forces during a collision are equal and opposite. Well, let's take it one step further. If those 2 forces are equal and opposite, then the 2 impulses must also be equal and opposite. And this comes from our equation J, the definition of impulse, is equal to F average delta t. Time is effectively irrelevant here. Delta t is the same, of course, for either one, so that's just irrelevant. But what we see here is that if our forces are equal and opposite, then so must be our momentums. Our impulses. So equal and opposite forces means equal and opposite impulses. If that's the case, we can take it a step further again, because the impulse momentum theorem that we introduced in our previous lecture, in other words, J is equal to delta P, meaning an impulse that you deliver to an object will change its momentum. Well, if the impulse is the same for both, but opposite, then so must be your change in momentum. So the momentums of your objects are equal and opposite as well. So think about what that means. Momentums are equal and opposite. So the momentum of object 1 is equal to the momentum of object 2. They just point in different directions. In other words, one would be positive to the right, one would be negative to the left. So what we're basically saying here is, again, consider the 2 balls on the right. If ball 1's momentum increases by a certain amount in the collision, then ball 2's momentum will decrease by the same amount. Again, because they are equal, but opposite in direction. So if one increases, the other decreases. So it's always by the same amount. So if you gain 10 kilogram meters per second for one object, then you're going to lose that much in the second. So what we say is that the total momentum is unchanged. That's just another way of saying it is conserved. So this brings us to the law of conservation of momentum. The law of conservation of momentum states that the total momentum, P, of an isolated system. So we do want to make a distinction here. Isolated systems are those with no external forces acting on them, meaning there's nothing outside from the environment changing what's happening. Because something else could come in and deliver a force to your objects from an external factor to increase the total momentum. But we're talking about isolated systems. So for our purposes in this course, the level that we're at, we don't subject ourselves to external forces. So it's irrelevant for our purposes. But we're saying that the total momentum is conserved. It stays the same. So if you write this as an equation, something that stays the same, it means whatever your initial value is must equal your final value. So we say P initial equals P final. This is conservation of momentum. Momentum P does not change. Initial equals final. So when you look at this, it's almost deceptively simple. P final equals P initial. In fact, it's almost so simple that you could ask yourself, how would we even apply this equation, right? Because what can you even do here? Well, careful what you ask, because this is a much bigger equation than it seems. This is very similar to kind of how we experienced Newton's second law, F equals ma. At first, it was just F equals ma, and that things were nice and simple. But then, of course, we started to realize, okay, things are way more complex than that, because the net force is the sum of all forces acting on the object. We had things like weight and friction and normal force and tension, and you get the idea, right? So our problems got quite complicated relatively quickly, despite it still being F equals ma. Well, same thing here. This equation expands very rapidly. First of all, because there's multiple objects at play when there's a collision. You need at least two objects to have a collision, right? So typically you have either 2 or 3 objects, meaning you need momentum of 1 final plus momentum of 2 final plus momentum of 3 final and so on equals momentum 1 initial, momentum 2 initial, momentum 3 initial. So the equation expands to however many objects you have. But also, it's a vector. Vectors can have components. So if it is a 2-dimensional problem, you have to look at both the x direction and the y direction. So I call this subscript mayhem. That's my name for it. The real version of this equation is now shown. We have to account for 3 different subscripts on each of our terms. 1, 2, or 3 indicating which object we're referencing, x or y to indicate which direction we're talking about. Are we talking about the horizontal x direction or the vertical y direction? And then we have to think of whether it's initial or final, before the collision or after the collision. So we end up having 3 subscripts for every single term that we have. So this is the real form of conservation of momentum. The good news, if there is any, is that you don't always have 3 objects. So for any collision where you have only 2 objects, you won't need the 3rd term. So that makes it easier. And then for any situation where it's linear, in other words, let me say, not linear but only 1-dimensional, then you wouldn't need the y direction. So you know, if it's just motion back and forth, you don't have to worry about the y direction. So the idea here is that it doesn't necessarily need to be the full set of equations every single problem. And so we're going to work on a couple different examples that show you what it's like with just 1-dimensional motion and 2-dimensional motion. So before we get to those examples, let's just introduce one more definition. There's a very specific type of collision that we will encounter in our second example. It's important enough for me to at least throw up the definition, and that is an inelastic collision. When we say a collision is perfectly inelastic, that means that the 2 objects will stick together and move with a single common velocity. The diagram on the right shows you this. Initially, there are 2 separate objects that are approaching each other. Mass 1 on the left, mass 2 on the right. They're moving toward one another. Then they inelastically collide, meaning they stick together and move together as if it's one single object. So it's almost like this turns into one single object that moves off with a single velocity. So that is extremely important. So the idea that it moves with a single common velocity plays a role in the work that we will do in a very short time. On the other hand, you can have the opposite of a collision, which is an explosion. So that is, a couple masses that are connected or attached, and then it explodes away and the pieces go flying out in different directions. We'll see that in our next example, or the third example. So let's go ahead and jump right into it. We saw the full form of conservation of momentum equation, so now let's work on our first example to show how conservation of momentum can be used to solve problems. Personally, despite the fact that there's so many subscripts to keep track of, I really love these problems. You can do a lot of really useful work by applying them. So to start, let's just go ahead and right off the bat, just write P final equals P initial, just to get us ready. So the problem says Sandra and David stand facing each other on frictionless ice. Sandra has a mass of 45 kilograms, and David has a mass of 80 kilograms. They then push off from each other, as you can see in the picture on the right. After the push, Sandra moves off at 2.2 meters per second. What is David's speed? Just as a quick side note, if this truly was frictionless ice, no friction at all, their feet would have no traction on the ground, which means if they weren't able to push off each other, they would literally not be able to move. Just because there's literally no friction. So they wouldn't have any grip between their shoes or skates even and the ice. But anyways. So let us expand this equation now. So not to call people objects, but we have two objects here, Sandra and David, right? So there should be two terms in our equation. So let's expand it. We should have the momentum of Sandra, I'm going to use S to represent her, in the x direction, because this is horizontal motion, final, plus the momentum P of David, D, in the x direction, initial. Final. Final is on the left-hand side. So they have two final momentums, and initially they are also separate. So we have momentum of Sandra in the x direction initially, plus the momentum of David in the x direction initially as well. So this is kind of the expanded form of the equation for this problem. Two people, so two terms in the equation, but thankfully it's one-dimensional. They're only moving horizontally, so we don't have to worry about the y equation here, which is always nice. Okay, well, if the problem or the equation wasn't long enough as is, keep in mind, we aren't given momentum anywhere in this. We're just told the mass of each person and the speed of one of them. So we don't know the momentums. So we have to make this equation even longer by writing m times v for each of the momentums. So this becomes the mass of Sandra times the velocity of Sandra in the x direction, final, plus the mass of David times the velocity of David in the x direction, final. Right? Because remember, momentum from our last lecture is mass times velocity. So then this is equal to mass of Sandra times velocity of Sandra in the x direction initial, plus mass of David times the velocity of David in the x direction initially. So this is now the actual true form of our equation. It looks awful, I'll admit, because there again are so many subscripts to keep track of, but all it is m times v 4 times. So with that, let's go ahead and see what we can do here to simplify this. Whenever you get to this point, where you have your masses times your velocities, I encourage you to ask yourself, are any of these terms equal to 0? You should always do that because typically, not always, I won't say it's a guarantee, but typically there's at least something that is equal to 0 that allows you to simplify your equation. So think about the context of this problem. Initially, both Sandra and David are at rest. They are not moving initially. They're just standing there. So the initial velocities of both of them are 0, and anything times 0 is 0. So this whole term and this whole term, both initial terms, go to 0. They're both equal to 0 because they're not moving. So if you want to make a note, this is because they are not moving initially. They're not moving initially, so their initial velocities are 0, and thankfully, the entire right-hand side of the equation is 0. So I'll write it again just for clarity's sake with the 0 plugged in. So we have on the left-hand side, nothing changed. So mass Sandra, velocity Sandra, plus mass David, velocity David, all this equal to 0. So the problem asks us to figure out David's speed. So we're looking for VDX final. All it takes now is algebra. VDX final, David's final speed. We subtract this ms term over. So we're going to subtract this msv term over to the other side. And then we're going to divide by md, the mass of David. So let's do that. We have negative, because we're subtracting the s term over, ms vsx final, divided by mass of David. So if we plug everything in now, we have negative the mass of Sandra, which is 45 kilograms, times the velocity of Sandra, which is 2.2 meters per second, divided by David's mass of 80 kilograms. Two things to note while we're here. We are going to get a negative value. That does make sense because look at the picture. If you're looking at this, Sandra is moving off at a positive 2.2 meters per second. So David is going to move in the opposite direction, the negative direction, to the left. So it does make sense that we have a negative value here. So sometimes negatives freak people out. It's okay. It makes sense in this problem. Now, you can also reason roughly how big this value should be. Because think about what this is. David is more massive than Sandra. He has more mass. So he's going to move slower because he's more massive. Remember, by definition, mass is a resistance to acceleration. So he's not going to accelerate as much, so he's not going to end up with as great of a velocity. And indeed, we get a value of 1.2 meters per second. So he's nearly double her mass, so he is nearly half as fast. And there you have it. Our first conservation of momentum problem solved. Now again, I understand it looks awful with all the subscripts. It takes some getting used to, no doubt. But just be careful with your algebra, and you should be okay. Just always keep track of those subscripts. It can be easy to lose them in the mix of all of them. Okay, let's go to example 2. Example 2 says Jack stands at rest on a skateboard. They have a combined mass, him and the skateboard, of 75 kilograms. Ryan then throws a 3 kilogram ball horizontally at 4 meters per second, and Jack catches it. What is Jack's final speed? Well, we're going to start the same way as we did last time by writing P final equals P initial, just to get us ready to know that this is going to be a conservation of momentum problem. Now, be careful. This is going to be what we called a perfectly inelastic collision, because Jack is catching the ball. So once the ball hits Jack, he holds on to that ball, and he's going to move backwards with the ball attached to him, like in his arms. So what this means is we are going to see them move with a common mass at a single velocity. So they move together, meaning there's only one final term. We'll say mass, or let me just write it as momentum first. So we have momentum of, we'll say, Jack plus the ball. That's going to be my subscript. So momentum of Jack plus the ball in the x direction final equals, initially, they are two separate objects. Jack is separate from the ball, so we're going to have two separate momentums. The momentum of Jack in the x direction initially plus the momentum of the ball in the x direction initially. So this is a little bit different than what we saw in the last problem because they stayed as two distinct objects before and after the collision. But here, they combine into a single final term. So keep in mind that at this point we expand even further because we're not given momentums, we're given masses and speeds. So this is going to be the mass of Jack plus the ball times the velocity of Jack plus the ball in the x direction final equals the initial values. Mass of Jack times the velocity of Jack, x direction initial, plus mass of the ball times velocity of the ball in the x direction initially. So same process, start with p final equals p initial, write it out for however many objects you have, and then expand it to mass times velocity. Same process that we just saw. Oops. Oh no, I just deleted everything. Can I undo? Of course not. Okay, well, I'm just gonna write what we had again. I apologize for that. So we had mass of Jack plus the ball times the velocity of Jack plus the ball in the x direction final equals mass of Jack, velocity of Jack initially, and mass of ball times the velocity of the ball initially. Sorry about that. So at this point, again, this is where I say take a second to ask yourself, does anything go to zero? Is anything equal to zero in this? Well, the answer is yes. Initially, the ball is being thrown at 4 meters per second, so the ball is moving, but Jack is just standing at rest. So Jack's velocity initially is 0. He's standing at rest. Right? So he's not moving, so he has no velocity. So anything times 0 is 0. This whole term goes away to 0, and we are left with a little bit of something easier to work with. So with this, we are now able to rearrange our equation. So just imagine this middle term is gone, so it's irrelevant. It's equal to 0. We're solving for Jack's final speed. In other words, v j plus b x final. We're looking for that term there. So if that is the case, let's rearrange our equation. All we have to do is divide by the total mass. So velocity of Jack plus the ball in the x direction final, what we're trying to solve for, is the stuff on the right-hand side of the equation, mass of ball times velocity of ball in the x direction initially, divided by that total mass, mj plus b. Okay, well, if that's the case, I'm going to get rid of my scribbles just for making it more clear. So if that's the case, we are now ready to solve this problem. We just have to plug in our numbers. Mass of the ball is 3 kilograms. The velocity of the ball initially was 4 meters per second. And this is all divided by the total mass. So it's the total mass, Jack plus ball, because again, he catches the ball and they move together. So this is going to be our, 75 plus 3 to give us 78 kilograms. So this gives us a result of 0.15 meters per second. Now, this is a very small velocity, but if you think about it, that actually makes sense. All he's doing is catching a ball that wasn't thrown particularly hard. So if you catch a ball standing on a skateboard, you're not going to go flying back unless Ryan is crazy strong. So you can expect a very small velocity and as a result of this problem. Okay, well, this brings us to our third example. This one will take some time to complete. In fact, it's going to take probably 2 slides of space to write everything out. So let's hunker down and prepare to work on our first 2-dimensional problem. So in this problem, there's a lot of stuff going on. First of all, it is 2-dimensional. We have a firecracker in a coconut, for whatever reason, blowing the coconut into 3 pieces as you see in the picture. Two pieces of equal mass fly off, one south and one west. So in the picture, one down and one to the left. Perpendicular to each other, each at 20 meters per second. The third piece has twice the mass of the others. What are the resulting speed and direction of the third piece? So we're looking for the speed and direction of V3 final. This third piece, how fast does it move and in which direction? There's a lot of work to be done here. But first, let's just get mentally ready. Let's try to extrapolate all the information we can so that we are ready to solve. So again, first of all, this is a two-dimensional problem. This involves motion both horizontally and vertically. So we will have to use an x and a y equation to solve this. Additionally, notice that all of the pieces are connected before they explode. It's a coconut, it's a solid piece. So it's one single object, meaning there's only going to be one single term initially. That said, the coconut is initially at rest, so that initial term is going to be 0 anyways. So, it's a 2D problem. Prior to the explosion, it's a single object, so a single term in our equations, but it doesn't really matter anyways because it's at rest. It is not moving initially, so that whole term is going to be 0. I'm going to write all this out, by the way, so I'm just trying to put all our information down in words so that when I write out my equations, you can refer to the words and perhaps make more sense of it. Well, we're also experiencing a very unique setup in this problem because the problem tells us no masses. It doesn't give us any mass, but it does say that object 1 and object 2 have some mass. We're just going to call it mass m. So these pieces both have a mass m. We don't know how big it is. We aren't told any kilograms, right? But we do know they have equal masses. So let's just call it some mass m. We're then told that the third piece has twice the mass of the others. So this is going to have a mass 2m, 2 times whatever mass the others have. That becomes important when we work out our equations. So let's go ahead and start the process of solving this problem. P final equals P initial. So let's first start with the x direction, because we're going to have to do both x and y, again, because it is a two-dimensional problem. So let's set up our conservation of momentum equation in the x direction. There are 3 objects, so 3 terms in our equation. We have mass 1 times velocity 1 x final plus mass 2 velocity 2 x final plus mass 3 velocity 3x final, right? 3 objects, so 3 terms in our equation. But remember, initially, prior to the explosion, it's a single piece. So I'm just going to call it mass 1, 2, 3 times velocity 1, 2, 3 x initial. Only one term because initially there's only one object, just the coconut. But as we just described, initially it's at rest. So this whole term is 0 anyways. It's at rest. So the whole right-hand side of the equation is 0. Now, be careful. Something else is 0 in this equation as well, but for a different reason. One of those 3 velocities is 0. The one that is 0 is that of mass 2. Velocity 2 is 0. Why? In the x direction, horizontal direction, mass 2 here, this piece here, is moving straight down. It's only moving in the y direction. It does not have an x component. So as a result, it is 0 for this equation. So it has no x component. I'll write that here. No x component. So that middle term goes away. That means we have very little left in this equation. I will rewrite it here. So we have mass 1, velocity 1x final. The middle term's gone, plus mass 3, velocity 3x final is equal to 0 because the right-hand side is gone. So we can solve this now. So let's go ahead and try to arrange this. We're looking for the final velocity. So v3x final. A little bit of algebra here. We have to subtract the m1 term over to the other side. So negative m1 v1x final divided by mass 3. Okay. Well, we aren't given how big each mass is. We don't know what m1 or m3 is, but we do know how they compare. Remember, we're saying that they have a mass m, right? m1 and m2 have some unknown mass. We're just going to call it m. So let's plug that in. So in this case, we have negative m times the velocity, which we're told is 20 meters per second, but be careful, be very, very careful of the direction it's moving. Piece 1 right here is moving to the left. So it's negative 20 meters per second. Because again, remember, objects moving to the left have a negative velocity. Left is the negative direction. So we add a negative 20 there, and then mass 3 is 2 times the mass of the others. So we don't know how big each individual mass is, but we do know that one is m and the other is 2m. M's cancel out. We don't even need to know what the masses are. They cancel out. This leaves behind negative 20 divided by 2. Negative 20 times a negative sign, so positive 20 divided by 2, or 10 meters per second. So that is the x component of the velocity 3. So if this is velocity 3 here, we just solved for, in fact, this technically goes all the way down, we just solved for the x component of it. We just found v3x final. Now, we want to solve for the y component as well, v3y final. So to do this, we set up the same kind of equation. I'll use just a black dividing line here just to kind of give some space. We're running out of it already. That's a really bad line, but you get the idea. I'm going to section this off and switch over to the y direction now. So let's write out our full equation again, but for the y direction. m1 v1y final plus m2 v2 y final plus m3 v3 y final is equal to the initial term, m123 times velocity 123 in the x direction initially. Okay, well again, we can see things go to 0. Initially, the coconut is at rest, so this term goes to 0 because it is again at rest. Something goes to 0 in this equation. We're looking for what is not traveling in the vertical y direction. Well, this velocity 1 here is moving straight to the left, which means it doesn't have a y component. So the velocity 1 in the y direction goes to 0 for that reason. So to avoid the buttons on the bottom here, I'm going to kind of work offset from the bottom left corner a little bit. So what's left behind is m2 v2 final plus m3 v3 final equals 0. Rearranging this, we find v3 y final is equal to, if you just look at some basic rearranging, negative m2 v2 that's y final divided by mass 3. So, same kind of process as before. We don't know each individual mass, but we do know one is just a mass m. We're multiplying this by the velocity of object 2 in the y direction. This is a minus sign here. So the velocity of object 2, so that was, in this case, in the y direction, this force is going down at 20 meters per second. So that is a negative value again, because remember, vertically, downward is the negative direction. So, negative 20 meters per second, all divided by the third mass, which was 2 times the original mass. Masses cancel out, leaving behind actually the same number, 20 divided by 2, or 10 meters per second. So what we've just found, I'm writing all over the place, but what we have just found is that, what color would work here? Maybe the green. 10 meters per second is v3x final. 10 meters per second is v3y final. So what we've just done is find the components of this new force, or new velocity. We now know the x component and the y component of that triangle there. So now it comes down to trig. Geez, when I look at this with everything on it, it makes me realize my handwriting is pretty great, pretty awful. That's not pretty great, it's pretty awful. So I apologize. If some of this is hard to read, I do apologize. This is also a new tablet for me, so I'm getting used to it. But anyways, if you ever have questions on what the heck I'm writing, just let me know. So with this being done, we have the two components, v3x final and v3y final, meaning we are now able to use this to figure out the overall value. So what we can do is basically realize, I'm going to draw this over here again, that we've constructed two sides of a triangle. We just found out the horizontal and vertical components of this triangle. So we found v3y final and v3x final. So we want to solve for the hypotenuse, v3 final. So we use Pythagorean theorem, our classic Pythagorean theorem. So v3 final, what we're looking to solve for in this problem, would then be the square root of each component squared. So v3x final squared plus v3y final squared. So if we plug this in, we have the square root of 10 meters per second squared plus the other one, which is also 10 meters per second squared. So what is that, the square root of 200? So that would give you approximately 14 meters per second. There's the first part of our answer. We're asked for the magnitude and direction. In order to get the direction, we've done this before, but it's been a while in our class. We're looking for the direction, or the angle theta. By definition, this comes from the tangent function. Because, again, if you recall the definition of tangent, it is opposite over adjacent, which is the y component over the x component. So, by definition, theta is the inverse tangent of v3y final over v3x final. In other words, this is the inverse tangent of, well, 10 over 10. Which comes out to be 45 degrees. So our overall answer that we finally arrived at is that the piece 3 is going to go flying off at 14 meters per second, 45 degrees above the x-axis. There's your full solution. So it takes quite a bit of work, and again, there are subscripts everywhere. But hopefully, by laying it out with a picture and separating x's and y's and everything, that makes at least a little bit of sense. But But of course, especially for my students, I am always available. So, if you ever have questions, you can email me, you can shoot me a text even, because I do give my phone number to my students if you need it, or stop by during office hours, of course, and I will help you however I can. So that is our lecture on conservation of momentum. At this point, let's kind of bring things back again and work on 2 end of lecture questions. Question 1. You awake in the night to find that your living room is on fire. Hopefully that never happens. I didn't write this one, just to be clear. Your one chance to save yourself is to throw something that will hit the back of your bedroom door and close it, giving you time to escape out the window. You happen to have both a sticky ball of clay and a super bouncy super ball next to your bed, both the same size and same mass. You only have time to throw one. Which one will it be? This is dramatic. Your life depends on making the right choice. Okay, well, we want the one that's going to be the most effective at closing the door. Which one's going to apply the largest force? Well, we want the one that's going to have the largest change in momentum. Largest change in momentum is what we're looking for. Remember, momentum is final minus initial, or change in momentum is final momentum minus initial momentum. So what we actually want is something that will bounce off of the door. So that means this super ball is going to be the most effective. So allow me to explain. If you have the largest change in momentum because it moves forward and then bounces back, that means by our equations that you have a largest impulse, J, by the impulse momentum theorem. J is directly related to delta P. Well, if you have the largest impulse, then you have the largest force being delivered. Because remember, J, I'll do a little error here, J equals F delta T. And then from here to here, we knew this because J equals delta P. So if you have a larger change in momentum, you have a larger impulse, which means you deliver a greater force to the door, meaning you are going to be more effective at closing the door if something can bounce off of it. So that is just kind of a series of steps in order to figure out how that might work. So with that said, let's go to our second question. A mosquito and a truck have a head-on collision, splat. Which one has the larger change of momentum? Okay, well, it's sort of a trick question because you always want to think that the mosquito would be impacted the most, but it's not. They are the same. There's a number of ways to think about this, but number one, just remember our law. Conservation of momentum. Momentum will always be conserved. So if we said, even in our notes, if one object gains a certain amount of momentum, then the other one loses that same amount of momentum. It is always conserved. So they have the same change of momentum. The only difference is one's gaining momentum, the mosquito, one is losing it, the truck. But they are the same amount. All right, well, that is it for our lectures on momentum. As always, I hope you learned something, and as always, I hope you have a great day. Take care, y'all.